Katja.
Okay, thank you. Am I speaking loud enough? Yes? Okay. So first of all, I would like to thank the organizers for giving me the opportunity to speak here. So this talk is based on work with Davide Gaiotto, Justin Culp, who is here, Brian Williams, Jingsheng Wu, and Matthew Yu, and some work in progress. Okay, so supersymmetric quantum field theories have BPS subsectors. So the idea of twisted holography is to study what are the holographic duals of these BPS subsectors. So we can restrict to a BPS subsector by a procedure known as twisting that I will explain. And the holographic duals that we will encounter will usually be B-model topological string theory. So B-model has a nice closed string field theory, which is the BCOV theory. Okay, so this is an example. For the n equals 4 super Young Mills has a BPS subsector, which is a 2D chiral algebra. Okay, we can get this subsector by a certain twist. And then the conjecture by Costello and Gaiotto is that this 2D chiral algebra subsector is dual to the B model on the complex manifold SL2C. So you can think about this as like an analogous BPS subsector of type 2B on ADS5 times S5. Okay, so this ADS3 sits inside S5, S3 sits inside S5, and this 2D chiral algebra lives on the boundary of ADS3. Okay, so the goal is to phrase this duality as an independent duality. So one motivation is that when we go to this BPS subsector, the dependence on various couplings drops out. So this makes it manifest how the geometry arises from the combinatorics of large n matrices. So for example, in this 2D chiral algebra, the dependence on the 't Hooft coupling drops out. So basically, there's just one parameter n, which is the rank of the gauge group that gets mapped to 1 over G string. Okay, the second motivation is that once we twist, the objects that we get are usually more well-defined mathematically. Okay, so this allows us to phrase some of the entries of the holographic dictionary using methods of homological algebra. Okay, so today I will talk about two examples of dualities in B-model. So one is this duality between the 2D chiral algebra subsector of n equals 4 super Young Mills and the B-model on SL2C. Okay, and the second example will be between 4D holomorphic theory and B-model in non-commutative spacetime. Okay, and today we will focus on the correspondence between determinant operators, so these are operators of order n, and so-called giant graviton branes. Okay, so in particular, I will show two things. We can match saddles of correlation functions of determinants with non-perturbative D-brane saddles in the back-reacted geometry. And the second thing, we can match determinant modifications with open strings on various branes in the B model. Okay, so supersymmetric quantum field theories have fermionic symmetry generators. These are the supercharges that we denote Q. Okay, so since they are fermionic, they square to 0, so you can take their cohomology. Okay, so twisting a supersymmetric theory is this procedure of picking a supercharge and restricting to its cohomology. Okay, so we take the operators that are closed, and we identify the operators that differ by something exact. Okay, so when we do this, this produces a subsector of the original theory, which hopefully is easier to study. So in this subsector, the dependence on certain spacetime coordinates drops out. Okay, so the supercharges satisfy anti-commutation relations roughly of this form. So these are the spacetime momenta. So you can see this momentum is equal to Q acting on something else. So this is exact in cohomology. Okay, momenta generates spacetime translations. So when we take cohomology, the dependence on certain space-time directions will drop out. Okay, so for example, if all of the momenta are exact, then we have the topological twist. And if half of the momenta are exact, then we have the holomorphic twist. Okay, so we might be more familiar with topological twists. So today we will talk about 2D and 4D holomorphic theories. Okay, and finally, so once we twist, it turns out that there's a lot of extra mathematical structure which becomes visible at the level of cohomology. So for example, there are these holomorphic symmetry enhancements to infinite dimensional symmetry algebras, but I will not talk about this much today. Okay, so now let's look at a particular BPS subsector. So for the n equals 2 superconformal theory has a 2D chiral algebra subsector. So this is defined by first we restrict to a 2D plane, and then we take cohomology with respect to a linear combination of a supercharge and a superconformal charge. So in particular, n equals 4 super-Young Mills has this chiral algebra subsector. So for n equals 4 super-Young Mills, this is a gauge beta gamma system. So first of all, there's a symplectic bosons, X and Y, with the following OPE. So these are the adjoint indices that go from 1 to n. There's a BC ghost system, and then there's a BRC charge. Okay, so we will use the following notation. We can combine these 4 fields into one superfield. So we define these odd spacetime coordinates, theta 1, theta 2, and we combine these 4 fields into this superfield. Okay, so n equals 4 super-Young Mills has this BPS subsector. So now we would like to ask what is the holographic dual of this subsector. So first we would like to realize this chiral algebra in the B model. Okay, so it turns out that this chiral algebra is precisely the word volume theory of ND1 branes in the B model. Okay, so they wrap C inside C3. There's 2 transverse directions, and these symplectic bosons X and Y, they parameterize the fluctuations in these 2 transverse directions. Okay, so now we can try to back-react these branes. Okay, so it turns out that this stack of branes sources a field called Beltrami differential, and this deforms the complex structure from flat to SL to C. Okay, so again, we have B model in flat space. We put a stack of ND1 branes, so they support this chiral algebra, and we back-react these branes. We get B model on SL to C. Okay? So you might be familiar with the geometric transition from the resolved to deformed conifold. So here we just start with flat space for convenience. So it's like a patch of the resolved conifold. Okay, so the holographic dictionary was developed in this paper. So for example, they were able to match single traces with deformations of boundary conditions on SL to C. Okay, and later we were able to extend this dictionary to include determinant operators, which are dual to so-called giant graviton branes. So in our case, these are the one branes. Okay, one could also consider non-conformal vacua of the 2D chiral algebra. So these will be dual to geometries that are asymptotically SL to C. So this is like a twisted version of the duality between the Coulomb branch of n equals 4 super-Young Mills and its multi-center solutions, which are ADS5 times S5. Okay, so now I would like to focus on this correspondence between determinants and giant gravitons. So let's consider a determinant operator in the chiral algebra. So this determinant is dual to a D1 brane, which wraps a line in Euclidean ADS and a circle inside S3. So the parameter Z is where this brane hits the boundary of ADS3. The parameter U controls the orientation of S1, and the parameter M controls the size of S1. Okay, so inserting a determinant is dual to an insertion of a D1 brane, which has the following boundary behavior. Okay, so now we could try to insert more determinants. So if we insert more determinants, that one could imagine that there could be more different brane configurations with the same boundary behavior. So for example, if we have 3 determinants, you could imagine that there would be a brane which connects them all. Okay? There could also be a brane that is partially connected. And you could also imagine that there's a saddle which is disconnected. So what we can show is that we can match saddles of correlation functions of determinants with these different brane configurations. Okay, so for example, this saddle would correspond to a saddle of a correlation function that mostly picks out this M here. Okay. So the method for computing the determinant correlation function was explained in this paper. So they were able to rewrite a correlation function of many determinants in the following form. So they introduced these auxiliary bosonic variables ρ, okay, and they can rewrite this correlation function as an integral over ρ of an exponent which is of the form n times the action that doesn't depend on n. Okay, so this is the action. So after this rewriting, now this is susceptible to the saddle point analysis in the planar limit. Okay, so we can write the saddle point equation for this action in the matrix form. And what we can do is we can match the saddles that satisfy these equations to holomorphic curves in SL2C using a spectral curve construction. Okay, and then we can identify these holomorphic curves with these dual D-brane configurations. Okay, so now I'd like to mention another entry of the holographic dictionary, which is the correspondence between determinant modifications and brane excitations. So by determinant modification, I mean something like this. Okay, so these are the antisymmetric tensors that are contracted with these matrices. And this is a double modification. So it changes, we change one X letter into identity and one X letter into Y. So there is a very convenient method to generate all these determinant modifications. So first of all, we fermionize the determinants. So we can write them as a Grassmann integral. We introduce these fundamental and anti-fundamental fermions. Okay, and these fermions can actually be interpreted as open strings that are between the original stack and the probe D1 brane. Okay, so these strings live here at the intersection. Okay, and after back-reacting this stack, this probe brane becomes the giant graviton brane, which is dual to this determinant. Okay, so now that we have these fermions, we can write mesonic operators. So these mesons are built of fundamental and anti-fundamental fields. So for example, these are two mesons. And these mesons are dual to the open strings on these probe D1 branes. Okay, so when we have these mesons, we can insert them into this Grassmann integral, and this gives us a modified determinant. Okay, so this could also be extended to powers of determinants and multiple branes. Okay, so we can use these mesons that are dual to open strings to produce determinant modifications. Okay, so in our case, these giant graviton branes are also D1 branes. So the open string field theory on these D1 branes is another chiral algebra. Okay, So the open strings on this D1 brane is a second chiral algebra that we denote with a tilde. Okay, this chiral algebra has 4 types of fields. Okay, so this gives us 4 towers of determinant of mesons, which modify the determinant. Okay, so this gives us a classification of all the BRST closed modifications of determinants. Okay, now this chiral algebra has a BRST differential. This BRST differential can be matched with a dual differential that acts on these mesons. Okay, so this dual differential controls whether a modification made out of multiple mesons is also closed. Okay, so if we do this single modification, it's going to be closed. Okay, but if you want to do multiple modifications, then we have to also take into account this extra differential. Okay, so for example, if we take an operator in the chiral algebra that's closed, it will correspond to a modification that's not exact. Okay, and if we take an operator that's not exact, it will correspond to a modification that's closed. Okay, there's also one-loop corrections to these differentials that can also be matched. Okay. So now I would like to talk about a different BPS subsector, which is the holomorphic twist. Okay, so the holomorphic twist of 4D n = 1 is defined as Q cohomology. So 4D n = 1 theories have 4 supercharges. So this Q cohomology captures the 1/4 BPS subsector. Okay, so for n = 4 super-Young mills, this is the 1/16 BPS subsector. Okay, so now the twisted theory is 4D holomorphic. Okay, so before we had a 2D holomorphic theory, now it's 4D holomorphic. And the operators that contribute to the holomorphic twist are precisely the operators that are counted by the supersymmetric index. And like I said before, these 4D holomorphic theories have this very interesting mathematical structures. For example, there are infinite-dimensional symmetry algebras, which are like a higher version of a 2D chiral algebra. Okay, so now let's look at the easiest example of the holomorphic twist. So that's the twist of pure 4D n = 1 super-Young mills. Okay, so the holomorphic twist of this is equivalent to the BF theory. Okay, so that's the action. There are 2 superfields B and C. Okay, the anti-holomorphic forms are hidden here. So this integral picks out the top form. Okay. So the field content of 4D n = 1 is just the vector multiplet. So we can match some of the fields of the vector multiplet with these fields of holomorphic BF theory. Okay, so for example, the holomorphic part of the field strength can be matched with the 0 component of the B superfield. The gauginos can be matched with derivatives of C. Okay, so the point is that this is a simplified theory which governs the holomorphic twist of 4D n = 1 super-Young mills. So in particular, the supercharge cohomology is equivalent to the BRST cohomology of the simplified theory. Okay, so now we would like to realize this again in the B model. Okay, so it turns out that this theory is the word volume theory of n D3 branes. So they wrap C2 inside C3. So there's one transverse direction, and this field B controls the fluctuations along this transverse direction. Okay, so again, we can try to back-react these branes. So in this case, they do not source Beltrami differentials, so they do not deform the complex structure. Okay, so they have a different effect. So the effect they have is that they introduce non-commutativity in the spacetime. Okay, so again, we have B model in C3. Now we put n D3 branes. So this is the word volume theory of these D3 branes. We back react them, and we get B model in the presence of this field that introduces non-commutativity in the spacetime. Okay, so this is like the easiest example of a duality between a 4D holomorphic theory and B model. Okay, so now we would like to add some matter. So now we want to look at the holomorphic twist of n equals 4 superangles. Okay, so this captures the 116 BPS subsector. So this was the topic of Chiming's talk yesterday. Okay, so in the n equals 1 language, n equals 4 superangles has a vector multiplet and 3 chiral multiplets. Okay, so the field content now is this BF theory and 3 beta gammas and a superpotential. So before we had a 2D beta gamma system, now we have a 4D beta gamma system. Again, we can combine all these fields into a superfield, and we can realize this theory as a word volume theory of the free branes, but now in C5. So there's 3 transverse directions, and these scalars gamma, they control the fluctuations in these 3 complex directions. Okay, so again, we can back react these branes, and again, the back reaction does not deform the complex structure. It again introduces non-commutativity in the spacetime. Okay, so one can also study the correspondence between determinant operators and giant graviton branes for these 4D holomorphic theories. So now the giant gravitons are also the free branes. Okay, and I don't have time to present this, but we can also get a classification of all the BRST closed determinant modifications in n equals 4 superangles using this correspondence with giant graviton branes. Okay, we can also do this just for the BMN subsector and for the holomorphic BF theory. Okay, so now I would like to mention some possible future directions. Okay, so these determinant modifications that I talked about, they give us families of BPS operators in n equals 4 superangles, also just in the BMN subsector. So these families depend on n. So it would be very interesting to figure out if they maybe account for some fortuitous states, or if they are all monotone, according to this classification presented by Chiming yesterday. Okay, after considering operators of order n, so it would be interesting to consider operators of order n squared. Okay, so an example would be a large power of determinants. So on the chiral algebra side, this would give us something like multi-matrix models. And on the holographic side, putting n determinants is dual to putting n giant graviton branes, which will back react the geometry further. And then a related interesting question would be how to twist things like supersymmetric black hole solutions. So for now, there hasn't been any work on this topic yet. Okay, and as demonstrated, so twisted holography can include non-perturbative saddles. So for example, this chiral algebra knows about non-perturbative D-brane saddles. Okay, and it should probably also know about saddles of order n squared. Okay, so there could be some interesting Stokes phenomena to be studied there. For example, one could study how different saddles, which different saddles dominate depending on parameters, and how these saddles sum up together. So this could be an interesting place to study things like sum over geometries. Okay, and then finally, it would be very interesting to develop further this holographic dictionary for the B model in non-commutative spacetime, which comes from back reacting the free branes. Okay, so that's all I wanted to say. Thank you.
Thank you, Kasia, for this nice talk. Any questions? Yes, Kumrun.
Nice talk. Just a few comments. The ADS3 times S3 that you mentioned, or basically the conical geometry that you want to mention, just in connection with the comments that I was making yesterday, that is dual to c equals to 1 at the self-dual radius. And the observables that you're talking about, which is the complex structure of the conifold, is the ground ring that was studied by Witten back in the day. So that's the connection between non-critical strings and Calabi-Yau and Kodaira-Spencer and all that in that context. But that's one comment. The question to you, though, is in the context of this duality, when you embed this duality in string theory, we did this with Rajesh and also with Robert. The way we did it was in the context of conifold. Namely, you had on one side, you had type 2b string theory with a P1. We wrapped D5 brane around P1, ND5 brane around T1. On the dual side, you get the analog of the conifold resolved. And that was interpreted by us in the paper with Robert as the gaugino condensation for n equals to 1. SUN Yang. So the physical setup is not n equals to 4. Rather, it's n equals to 1 in 4D. So I'm a bit puzzled about why you're talking about n equals to 4 in this context.
Well, so the conjecture is that the 2D chiral algebra is dual to this B model on the form conifold. The 2D chiral algebra is a subsector of n equals 4 super-Yang mills. Okay, so like the conjecture is that you can embed it into the full duality between n equals 4 super-Yang mills and string theory and ADS 5 times S5.
But conifold, I mean, if you in any way you embed this in the full string theory, which is we embedded it, you always break supersymmetry, and you break it down to n equals to 1 in 4D. And so there is a transition, like, you know, Klebanov, Strassler, and all that study. That's the context. The physical context of this conifold transition is the 4D n equals to 1 confinement, and the S3 that we are talking about is the gaugino condensate. So that's the physics, not n equals to 4. Now, you might have a mathematical similarity between them, but I don't think it embeds that way.
Okay, so maybe the difference is that, well, I want to say it's an embedding, like it's a twist of this 10-dimensional string theory or supergravity. So like the map is not very easy. So for us, it's easier to start with the twisted theory and back react. And we don't really ever like localize from the full string theory into the B model. But it would be interesting if it was possible to do some of these localization computations.
I think it would be interesting to do it in that context, yes. Thank you.
Okay.
Sorry, I think that localization question was studied in our paper with Bonetti, right? We started from the ADS5 story and at least and the space-time level showed that there was this localization to the ADS3 subset. Okay,
so there are some localization computations as well, yes. Thank you.
Any other questions? Comments? Yes, please.
Yeah, so thanks very much for the talk. So maybe this is not unrelated to Coleman's question. So for n equals 4, there is, of course, a topological B model on twistor space, which was constructed by Witten. And I was wondering whether there is any connection that you understand between the topological B model on twistor space and this construction.
So there should also be like a twisted holography version for that, but it hasn't been studied yet, so I'm not sure what is the connection. Sorry.
Okay, thanks.
Any other questions? Yes.
Is there some connection between the twist in the boundary and twist in the bulk in examples like in ADS3 cross S3?
Yeah, so like the point is that like doing the twist on the boundary should correspond to doing in the twist in the bulk. So for example, when you put the branes in the twisted bulk, the branes will be twists of the branes in the original theory. So you can match things like that.
Yeah, in particular in ADS3 cross S3, the black hole entropy can be computed by doing localization in the bulk by using a twist in the bulk. And I'm wondering whether there is a direct relation between the two twists.
Yeah, so these localization computations should be related to this. Yeah, but we haven't done any localization computations.
Okay, I'm just saying. Okay, I'm pointing out that in ADS3 context, in supergravity, bulk localization has been done.
Okay, thank you.
No, go ahead.
So, in the context of a holomorphic twist, what are interesting observables to study, apart from just state counting?
Yeah, okay, so the holomorphically twisted spheres have these observables that are called lambda brackets. So there usually isn't correlation functions. So when you take correlation function of two operators that are in the same 116 BPS subsector, it's usually 0. Okay, but you can define these other observables, lambda brackets. So these are defined using descent relations. So you can integrate over as free forms. Okay, so even though there's no correlation functions, there are still interesting observables. And also, you can use these observables, you can use these brackets to define these infinite dimensional symmetry algebras. Yeah, so this should also, it would be very interesting to match this to the holographic computation in the BCOV Fourier.
Hi. So I guess this is not really a question. But this first question that you have here, what is your intuition for it?
So I would prefer not to commit to either option. Okay, but the point is that if you take a determinant, if you change n, the determinant is getting longer. So it will not be, this determinant modification will not give you the same operators for each n. It will give you different operators with different quantum numbers. But it does define a family that depends on n. Yeah, but it could be possible that they are all monotone. So I don't know this yet.
Any questions from the Zoom? No? Maybe that's a good point to thank Kasia again for this.
Thank you.